Okay. Hello, everyone. Welcome to this fifth edition of the Young Frontiers meeting. We are very happy to have you all here today. Okay, in any case that you have any questions or comments, you can ask me or Matias Sempe and Miroslava Mosso, we are the organizers, and we will be in the chat. So let's start with the first lecture. So Nico Kamensky, all yours.
Okay, hi everyone. First of all, I want to say just 2 words to thank the organizers for making this happen. I'm very happy that this is becoming a really nice tradition. I'm very happy that many people are showing up, and that and I'm very happy how all of this is turning out. I think it's a really nice event for all of us coming from, or many of us coming from Latin America. So I want to thank the organizers for asking me to be the chair for the first session because it's an honor. I want to thank the speakers, Mauricio, who's going to start now, and Angeli and Javier for agreeing to give the courses, which I'm sure will be amazing. And so, without further ado, I want to introduce Mauricio Romo from Tsinghua University, and he's going to talk to us about supersymmetric localization. So, please, Mauricio, all yours.
Thanks a lot for the introduction, Nicolas. Just a clarification. So now I moved to Fudan University, but it's okay. It's a small detail. No, thank you very much for the invitation. Great initiative to do this kind of thing. If anybody, please let me know if anybody sent any question in the chat, because probably I won't be able to see the chat from here. I will put, so I will make my screen. Let's see, I think, yes. So let me put full screen. So you can see the screen. I guess now you can see more, right? No, let me know if there is any problem with seeing the screen. Probably I will turn off the camera because you will see only the floor anyway, the ceiling. Okay. So this series of lectures was supposed was have in mind that the audience is not really expert in this topic. Like I assume there are many grad students or maybe early postdocs that are not working in this topic, but that they are interested to learn one thing or two about this. So I did the talks, I planned the talks that way. So let me give you a very rough outline that you can probably find on the web page. So the outline is like in the lecture one, I'm going to talk about some theories, some families of theories called gauge linear sigma models, or GLSM for short, so we don't have to write this all the time. And so we are going to give some general aspects of it, and their deformations. In particular, we are going to talk about marginal deformations. And their relation with geometry, which is, in other words, the idea of the first lecture. There's not going to be any supersymmetric localization computation, but we are going to set up the stage and also, most importantly, explain why we care of in such theory. Because of course, many times one does things just because you can, but in this case, I think it's very important to say why there is a strong relation with algebraic geometry that is our main motivation to actually work in this kind of theory. So the second thing, the second lecture, so this 1, 2, 3 are the number of lectures. So on the second lecture, I'm going to talk more about supersymmetric, which we abbreviate by SUSY, localization. SUSY localization for the class of theories we are going to talk about, which is a 2,2 two-dimensional theory. two-dimensional theory. And this will be a sketch of computation, of the computation for the worksheet being in the case in the sphere, which mostly probably will be very sketchy there because that result was done by other people, and I will also focus on the case of the worksheet being disk. Or so this what we call hemisphere, because we use the disk with a particular metric, but it's topologically it's just a disk. So I will focus probably more on this one, on the second one, because that was my work with Kentaro Hori, now more than 10 years ago, but still many applications are possible from that work. So that's it about the second lecture. So that probably will take quite a while. And on the third lecture, I'm going to talk about applications. So, or continue if we have something left over from lecture 2, but then I'm going to talk applications to algebraic geometry. So why those correlators can help you actually to predict results or to make conjectures in algebraic geometry. I don't assume that the audience is expert in algebraic geometry, so don't worry. But yeah, but this is very important to emphasize the mathematics behind, because that's why we are doing what we do, at least in my line of research. So let me start very basic then. And as I said, interrupt me at any point, but you have to let the moderators to, you please let me know if there are questions. So we are going to start then talking about GLSMs on flat space. Flat space, which will be that means flat space in R2 or R1,1. At the end, all the computations are done in Euclidean space. The difference is not very dramatic for the case of the sphere of the disk. Of course, if you are doing other type of computation, it's very dramatic if you are going to use Minkowski or Euclidean signature. But in this case, it's like very simple going from one to the other. So I'm going to remember you what is the supersymmetry that is involved in this theory. By the way, also I assume that my audience is mostly composed or almost all completely composed by physicists. So I'm not going to explain the mathematics behind certain concepts that are natural from quantum field theory. So in this case, I'm going to remind you what we call the n equal 2,2 supersymmetry algebra. Because on R,1, so the supersymmetry algebra on R,1, this is the symmetries of our theory. So the most important thing when we study a quantum field theory to know the symmetries of our theory. So in this case, is 2,2 supersymmetry. So 2,2 supersymmetry is just an extension or a supersymmetric extension of the Poincaré. So these three generators I'm writing here is the Poincaré group in R1,1. So this will be the Lorentz rotations are called M. The translations, spatial translations are called P, and time translation are called H, as usual. And they satisfy the following commutation relations that are going to become important later. That are these. So this is just ordinary Lie algebra, but we know that if we extend this to supersymmetry, we extend it supersymmetrically. That means we add odd generators. It becomes a super Lie algebra, so it becomes a two-graded, and we have to add odd generators that we call the supercharges. So this is a Q. I'm going to denote in Q plus minus, Q plus minus bar. So the bar has nothing to do, just so we are clear. The bar has, in this case, has nothing to do with conjugation. This bar is just traditional name for this supercharge. So two are called Q plus minus, and the others are called Q bar plus minus. So the bar for most of this lecture, the bar just, you can take it as a name, nothing to do with any type of conjugation. So these are odd, as I mentioned, these are odd or Grassmann values, oddly graded generators. And the only commutation relations that are relevant are these, or sorry, these are the only that are non-zero. So first this one, and this one. So you can see this plus and minus sub-index of the supercharges are actually associated in the flat space. Is not, you can think of it kind of defined by this bracket if you want, by the Lorentz rotation. If you are in curved space, as we will see, or as I will remind you, this plus minus means they are sections of the two spin bundles. So it's plus and it's minus. And I'm going to go back to that later. All these commutators, the commutators between now supercharges and the previous Poincare group, they have to be graded. So we have also the commutator between the two supercharges. The only non-vanishing ones are these, and I denote, usually in physics, we denote with these brackets, these different brackets to indicate this is an anti-commutator. So the collection of all the commutator is graded. So usually for anti-commutators, we do this other bracket, we write this other bracket, and this is it. So these are this is the basic supersymmetry algebra. There are two more symmetries we can add. So in addition, we have the other symmetries that are called R symmetries. So R symmetries are a very special kind of symmetries that appears once you extend supersymmetrically any of the Poincare group, Lie algebra. So the R symmetries are very special because they are not like the ordinary, like internal symmetries, because they commute. They commute. The commutator with the supercharges is non-trivial. So that's why they are not internal symmetries, and the R symmetries can be present or cannot in your theory. In the theories we are going to talk most of these lectures, they are unbroken. They will be unbroken and they will be non-anomalous, okay? So the R symmetries in this kind of theories will be U1 cross U1 subalgebra, also U1 sub U1 subgroup, form this R symmetries from a subgroup. These are the generators of U tilde vector. So this, my notation, when I put this tilde down the letter, I mean Lie algebra, okay? This means Lie algebra of U1 vector. So usually one of them is called vector, one of the other is called axial. Sometimes we go to other bases where we call them left and right. Generators of U1 vector or U1 tilde, sorry. Yes, U1 tilde axial. Okay, so the generator, I call it FAFP, and they satisfy the following commutations. So Q plus minus equal minus Q plus minus B. So as the lectures advance, I will be maybe on some, I cannot be that detailed, of course, otherwise we'll never finish, but I think this basic concept is good to show you with all gory details sometimes. And this okay, so as I said, there is other bases, sometimes left and right, but for the purpose of this talk, it's better to use axial and vector. One thing that's important, that's going to become very important later, and maybe some of you are very familiar, that this Lie superalgebra or the supersymmetric algebra has there exists in it two nilpotent operators that are going to appear sometime again. So I'm going to define them. One is called QA, which is this combination, and you can check yourself that these guys are nilpotent. That means if you square them, they become 0. And the other is called QB. So these are names coming from very old times, from the 80s, from works of Witten. So this, and of course, there is, you can have also the conjugate of these operators, conjugate in the sense of charge conjugate. Or if you want, this is the definition also of my conjugate, this dagger. So definition is just, you can take it as a definition. Okay, so this was the axial. So remark is this one remark. The other remark is in order to get the SUSY algebra, or I should call it the 2,2 SUSY algebra in R2. So Euclidean, just perform the weak rotation. So you have to send you define the x2 coordinate as the I times the x0 coordinate. Okay, that's leave it as a homework if you want. And as I mentioned again, the U1, the R symmetries, this axial and vector, sometimes can be broken in some theories, and theories where they are broken, they're still very interesting. Theories where there's only one of them also are very interesting, but in this case, the theories are that we're going to see both are unbroken.
Sorry.
So, yes.
One question. The generators, this definition QA dagger and QB dagger are the same, or is
I'm sorry.
Okay, thank you very much.
No problem. Yeah. Okay. Thank you for the question. So now we are going to, okay, there are many theories that satisfy these symmetries, but of course we are going to talk about GLSM theories. So its GLSM theories are 2,2, so it has this symmetry algebra, 2,2 gauge theory. So just if you are familiar, you probably should be if you are a particle physicist. This is called a linear sigma model because it's a sigma model, of course, with a linear target. So the target is really trivial, okay? It's just a linear place. But the gauge, the complication of the theory, the reason we can relate it to very, very non-trivial geometries comes from other data of the theory. So GLSM theories, these theories can be specified, I should say, in flat space, so R2 or R1,1 in flat space by the following data. Or data means choice. So these are things you choose. And after you choose these things, you can write a theory. So what are these things? So it's a quadruplet of things. One thing is our gauge group, which all of us, most of us, sorry, probably think when they think of gauge theory, most of the gauge theory you think it's a, it's a compact Lie group, okay? Going to be, and in all this talk is going to be a compact Lie group. Probably many examples going just to be torus, a compact Lie group. we need to specify a representation that I call rho, a representation of this Lie group. Okay, and the representation, as you know from group representation, it requires the specification of a complex here. This is a complex vector space. So this is the linear target. And this representation, essentially, I'm telling you what are the gauge transformation, how my matter transform under gauge symmetries. And I can specify two more things in this theory. One thing is because my target is linear, so it's non-compact and very trivial, I can in principle have also in my theory a potential, or sometimes called superpotential. So this is called superpotential, which is a function from B to the complex number. That is also, it's required to be gauge, or I should call it G invariant. You are more formal, you can say that the W belongs to the symmetrization of the dual, and you take the G invariant part. But if that's too alien to you, don't worry. Just a remark. If not, it's just a function with which is gauge invariant, and it's a holomorphic. That was simply invariant and it's holomorphic. We also can specify something called twisted superpotential. If you are familiar with GLSMs, don't get confused. This is not the effective twisted superpotential. Actually, we are going to set the twisted potential to something extremely simple on all the talk. And that's usually what people mean in this case. So this is again, is my notation, the algebra of G, and complexified this you see. So it goes from this vector space to the complex numbers. Okay, so we need to specify all these things, and we can write the theory after we specify these things. So now I have to explain you a little bit more on how these things comes together. But before, I have to tell you a little bit of more properties. So you probably can see now how the theory comes together, right? You have a gauge group, so you have gauge multiplets, and you have a representation of the gauge group that is specifying how the matter transforms under the gauge symmetry. Of course, I'm going to do an example at the end, but it's important that you see that this is the family of theories we want. I should say to its potential, this is both are G invariant and holomorphic, of course. So now I have to talk about some properties. So if you want to learn more about the GLSM, there are many sources. One of my favorites is the Mirror Symmetry book, the volume 1, the one edited by Hori and many other authors, Bafaklian, etc. That's very nice, but if you want to go to the origins, of course, a great paper is Witten's paper from 93, which is called Phases of Unequal Two Theories in Two Dimensions, or something like that. So what we learn, one of the things we know about these models is that written like this, you need a little bit more work to know, as we said, if we can we preserve, why that move like that? Can we have unbroken R symmetries? And the answer is quite a bit of work, but you can go to a paper of Witten or to other reference. So the answer is that first, let's talk about the vector. So FB is unbroken, provided this W is quasi-homogeneous under this. So let me write it like this. So what this means? So this just means this is R is the weight, or in physics we like to call it the R charge of our field phi. The fields phi are the coordinates in this vector space. I write it like this. That's because we are between physics. If not, I have to write B dual, but they are the coordinates on the vector space B. Remember this vector space appearing here on the representation. So yeah, you want this W to be quasi-homogeneous. So that's what makes the phi unbroken. Quantum and classically. So this is enough. Okay. Axial is a little bit more subtle. Fi is unbroken. So there's several subtleties here, provided the representation factors through SLB. And we are going to set. So one is that it's the representation factors through SLB. That's make it unbroken. But you also need some more conditions on W tilde. But we are going to set W tilde a linear function. Linear function. We are going to set it a linear function in order not to have to worry about some extra stuff. So when it's a linear function, provided that this holds, it's unbroken. Okay, so that's the thing. So after specifying such data, so we are going to consider it linear. So maybe I can set now immediately this. So I will write it like this, and where sigma, as I said, sigma belongs to this space, right? Sigma belongs to this space, and T is an element. T actually is an element on the, where T is an element of the algebra of the center of G. This is the center. And you take the dual and complex equation. So a lot of it. So this is the note. I denote it like this. So if you choose a basis, if we choose a basis for these vector spaces, this vector space, T of sigma, you can write it like this, right? Linear. So and T are called phi for Collier-Iliopoulos, theta parameters, and written as T, usually this. You write like this, the real part, so this is the phi, and the imaginary part, you call it theta. That's where theta parameter come from, the name. So that is the twisted potential we are going to work with. So that, and these properties I said above is what guarantees that the R symmetries, the two U1 R symmetries, are completely unbroken, and we are going to always assume all these holds. You can generalize it when these conditions are not true, but then some things work, something works very differently. So better we are not going to go too much into that. So now after specifying search data, we can write a very explicit 2,2 gauge theory. For the supermultiplets, so supermultiplets or the representations, representations for our supersymmetric algebra that are given by the following. So one supermultiplet, it has the lower component is scalar, and it has these fermions. So this is my fermions. And it has an auxiliary scalar. So this is an auxiliary scalar. This thing is called a chiral multiplet. And associated to, so it's a chiral multiplet. So transforming, so we can say transforming in the representation of that we specify, right? So, and what else we specify? We specify a gauge group. So we have a multiplet, a vector multiplet. So this is the vector multiplet. So this is the vector potential. The connection on the gauge group. These are our fermions of this. And this is the twisted chiral. You can interpret it as a twisted chiral, but this is it's a scalar. This is scalar, and this is an auxiliary scalar. This is complex, by the way. It's complex value. But this D is real value. Okay. And this is so-called vector multiplet. Very good. So, and if you, it also, of course, is not transformed on trivially under the gauge group. So it's sigma and D and lambda transform in the adjoint representation of G. And B mu, of course, transform as a connection. Okay, so that's it. Those are the multiplets. And now I should maybe say a word or two about the infrared dynamics. But before that, let me say the Lagrangian for these multiplets. Take the form. So I'm not going to write all the Lagrangian because that will take all the rest of the talk itself. But the Lagrangian of this GLSM is good to remember. It kind of has a sum of three parts. One is the kinetic term for the chiral fields. So here in the kinetic term for the chiral fields, you have is the gauge derivative of phi. You have like these kind of terms, etc. And you have some coupling. You have some couplings between the phi bar, the chiral, the scalar, and the other fields. There are some couplings that take this form, which is the D field on the vector multiplet, and you have something like sigma bar phi. Schematically, they have this form. Plus dot dot. You have a kinetic term for the gauge multiplet. So the kinetic term for the gauge multiplet, which I will write in a second downstairs, a few terms. And you have a term that depends on the superpotential. You have a term that depends on the superpotential and a term that depends on the phi parameter. So let me write some of the simple terms. So here, not to make a mess. So the gauge kinetic term, this thing is something like this. So you have a kinetic term for sigma, and you have some couplings like this, and like F of sorry, maybe I should have written a different way. So this plus B 1 2 square, where the is minus the I. Yeah. So you have some terms of this form, and then some fermionic terms that involve fermions are going to be very complicated, very important. But it's important that you see, if you have never seen this kind of theories, that the reason I'm writing this is to show that the sigma couples to the phi has a mass, and for example, and D, this auxiliary field D, doesn't have any derivative. There's no derivatives of D on the action, also not on the fermionic part. So that's why they're called auxiliary. They can be integrated out. The term that involves the superpotential is going to be actually very important before, and it takes this form. I'm writing it now explicitly, the coordinates. Every time we write phi, we mean like phi1 dot phi n, the coordinates on the vector space. So it takes like this, plus complex conjugate, plus some Fermi terms. These terms, are going to become relevant, and the phi term takes a form like this. Minus phi. And there's no more. This is exact. So this is B. So I should write B also B. Okay, so those are the terms. If you have never seen these theories, here you get a flavor how they couple. Here and the phi term, you see it becomes really simple. It's almost a topological term, and it involves no fermions. All right, so now I should tell you how spatial theory is related to geometry, why we care so much about this family of theories. But it's a good time to maybe ask if there are questions. If not, I will just continue.
Sorry, I have a question.
Yes, please.
You said that these were gauge linear sigma models.
Yes.
What is the symmetry that you are gauging, and what are the equivalent of the gauge fields? Or
very good. Very good. Yeah. Sure. No problem. I can tell you. So the symmetry I'm gauging is this G. So all the fields, all this row, transform under G by the representation that I specified. This representation. You usually, okay, if you are very, you wanted to take it to be faithful, by the way. You are very worried about that. So that's the gauge symmetry. G is the symmetry I'm gauging. And I took explicitly these functions W to be G invariant, precisely because I want to gauge.
Okay.
Okay.
But
so,
when you in my mind, whenever you have a symmetry and you want to gauge it, you introduce a gauge field.
Yeah, the gauge field is this one.
Ah, perfect. Thanks.
Sorry, I call it B mu. Yeah, maybe you can call it.
Okay, that's fine. Thanks.
I get it. Yeah, that's it. So yeah, so maybe in that case, so also this derivative, when I write the mu, I mean like this. Gauge covariant derivative.
Perfect. Thanks.
Okay, no problem. Thanks for the question. Okay, so now in order to tell you, okay, so far what I did, I wrote a theory. I told you it has some amount of supersymmetry. I told you it's a gauge theory. Like everything was very ad hoc. I just choose everything, but I want to tell you now a little bit why this theory is actually interesting, because so far there's no reason why you may think the theory is interesting for any person interested on the real world. Maybe it's not that interesting because it's supersymmetric. Maybe, well, two dimension can be very related to the real world, but supersymmetry not so much. And also I impose many conditions that make the theory to have a lot of supersymmetry, 4 supercharges and plus this R symmetry. So now I'm going to tell you why actually such a theory can be interesting, or I'm going to sketch it. Again, good reference for this is Witten's original paper. But here I'm going to sketch. So integrating out, after integrating out D and F, the auxiliary fields here you see F, here you see D. Integrating of D and F, we can show, or one can show, this theory has a classical potential given by. So what is the classical potential of this theory? So you just integrate and you just look at your Lagrangian, what you have that's not kinetic depth. And I'm going to write it classical, I should say, so. Of course, it's the bosonic part that I'm interested because I'm going to think, I'm going to study the classical path. So the potential looks like this. In many cases, it's better to study the, if you are not familiar, it's better to start looking at the abelian case. Of course, it's less complicated. Okay, the pen battery seems to be low, but let me charge a little bit of this. 1 second. Okay. So the this potential look like this. I'm going to write it. Okay. This that mu of phi is the Hamiltonian map, Hamiltonian moment map associated to Rho. If you are not familiar with the moment map associated to the action of a group on a vector space, it's okay because I'm going to show you some examples. The only thing that's important for you to know now is that this mu of phi is a real function. Mu of phi is a real function, and it goes something like phi of this one. It takes something like this one. Guys, I'm going to give you one example to for this where this Hamiltonian moment map is going to appear explicitly. So the classical vector is given by u equal to 0, right? You take a classical bosonic potential and you make it 0. That's the classical vector. And this, because it's a sum of positive real terms, this becomes actually, it looks very, very complicated, but indeed it's split into simple equations, which are these ones. So, by the way, this one is completely equivalent to the this is this, okay. All right. Very good. So that's those this is u equal to 0 actually split into very simple equations. So now maybe I would think to finish off this lecture or to do the last thing we are going to do instead of doing it from here. Instead of continue with this general case, I will show you an example. So example of solution to W sigma pi equal to 0.
Mauricio, sorry for the interruption. Just to let you know that you're entering the last 5 minutes before the questions.
I know. Don't worry. Yes, I'm aware. Thank you. I will just show you one example which is this one. To SLB given by lambda goes to lambda minus n lambda like this. B is C to the n plus 1. N plus 1, do I have n plus 1? So, and my right, n plus 1, right. So this should be, yeah, perfect. So this is, no. So, yeah, n plus 1. Yeah, now it is in SLB, determinant 1. So now I specify now to take these fields P. I will call the fields like this. This is like a name, typical name. We go x1 to xn and P. So these are my coordinates. So these are going to be the scalars of the chiral. Then W is defined to be P times Fn of x. So this is an homogeneous polynomial of degree n in x. So you can check it is integration invariant, and then this right. So now there exists W tilde is going to be just T. Now it's just ordinary. It's only one T and only one sigma. Because it's U1, right? U1, the center of U1 is just itself. It's an abelian group, right? So that's it. So now the Hamiltonian moment map associated to such a group action. That means rho takes the form mu of phi is, no, this is phi. Okay, that way. So it's like minus n norm of p square plus sum over I1 to n, etc. That's the moment. That's the Hamiltonian moment map. And we have now that solving, and it maybe you are homework, solving U sigma phi equal to 0 gives sigma equal to 0. Just sigma equal to 0. And mu this is and phi belongs to mu phi equal to zeta intersects with I will write it now explicitly. So Fnx equal to 0 and P times df dx I equal to 0. So this is for I equal 1 to n. So it's a collection, it's a set of equations. Provided, so this is also homework for you, provided theta is non-zero. Okay, so this is identical. So that's the solution to the classical equation. I think my time is over, but just to give you something for the next, from what we are going to start next in the next lecture. I will give you the final result, and you can show this in your case, in your when you are alone, like you can try to compute this. So if zeta is positive, then the solution is that x belongs to the Fn x equal to 0 intersected inside Pn minus 1. Projective space, this is, okay, this, I mean this, okay, it's the same. X and P equals to 0. And if Z is less than 0, then X equals, X is identically 0. And the solution is just, sorry, X 0, P is 0, P is fixed to some value, P is like something like Z over N, I think something like this. And this is just a point, it's just a point, the variety is just a point mod Zn plus 1 with a Zn plus 1 action. Okay, these are the solution to the classical equation. So I will stop here, and next time we are going to localize the theory and argue about more relations with geometry. Yeah, thank you.
Thank you for the really interesting first lecture, Mauricio. So we have about 8 minutes for questions. So please feel free to ask. Go ahead. Don't be shy.
So I will start. When you are looking for the BACWA in a non-abelian group, it's like the BACWA, you choose like the abelian part of the group, right? Or something like that.
Okay, when you are looking for so I have to mention something to one remark here, is these solutions to this. This is what we are going to call classical BACWA, okay?
Yeah.
So for the case of a non-abelian group, the BACWA had to be, of course, this. I mean, this, even for the abelian group, these solutions, you have to consider them, of course, modulo the gauge group, right? Everything has to be quotient by the gauge group. So in the case of the non-abelian group, it can happen that this quotient is very ill-defined. But no, you don't want to take just something like the Cartan subalgebra of the non-abelian group. You have to consider this is the whole, this is the complete gauge group. You don't want to consider a subalgebra, no. Even on the non-abelian case, it's the whole group that you are quotient.
Yeah, but when you wrote the BACWA, you wrote like sigma, the commutator between sigma and sigma bar.
That's correct. Yeah. That's correct. Yes.
And that's like the abelian part, right?
That means sigma belongs to the abelian part. Yes.
Yeah, but you're breaking the part where sigma belongs, because sigma was in the non-abelian part at the beginning, right?
That's correct. Sigma is the non-abelian part. and that's breaking the those points have are of course those points are not invariant under the gauge group action. But also here, look, in the example I give you, these points, all these points are also not invariant under the gauge group action. Like the gauge group acts non-trivially on phi as well.
Okay.
So you have to quotient, like it's a quotient manifold that, as I said, it can have a very nasty geometry, like it can be very badly defined.
Okay. Thank you.
Mhm.
Okay, any other questions? I already see Carlos's hand. Any other question? Any other urgent question? Feel free to ask. Okay, if not, Carlos, go ahead.
Mauricio, thank you for the lecture. May I ask you something a bit more generic?
Yeah, sure.
At some points during the lecture, you hinted at applications of the things you will be talking. Can you tell us in 2 minutes what applications you have in mind, things like those?
Oh, sure.
Theoretical physics, right? Not to I don't know, a falling apple, but to this kind of things.
But you want to know some particular application or
some application that comes to your mind because you almost mentioned something and then you kept on going. So
that's right. I hold on the application. So I have to I essentially have my applications are mostly in base of applications conjectures to generate, if you want, to generate conjectures on algebraic geometry from physics. So basically, the applications, so where the applications into mathematics come from, is because this comes from the invariance of certain correlators, certain open or closed correlators under marginal deformation. I can tell you specifically what deformations I have in mind. The deformations I have in mind mean varying the phi parameters or coefficients in W. I can set coefficients in W and W tilde. So, for example, I can give you an example. If we vary T, the space, I will call it the space of supersymmetric boundary conditions, I have to say of type B. So the boundary conditions that preserve something like QB that defined before. This space of boundary condition is invariant. Okay, so this can be interpreted. So this has a mathematical interpretation. This can be interpreted as what mathematicians will call equivalences of triangulated category. So triangulated categories is something that you can actually rewrite if you study supersymmetric boundary conditions of this type. So if you want this variation of this parameter gives you equivalent between the spaces of boundary conditions, and at the same time, this space of boundary conditions has a mathematical interpretation, like something associated to a geometry, for example. For example, if in this case, if I choose these 5 parameters, theta positive, and let's say some theta, for this sigma model, the space, the B type, for this sigma model, the B type boundary conditions are interpreted mathematically has this something called the derived category of coherent shapes of this hypersurface. And this is something really interesting in mathematics. I mean, something that has been studied for many years. So this is one application I have in mind where I go from something I understand from physics to make a prediction, if you want, in mathematics. Is that okay, or you are looking?
Thanks
for
very much.
some,
Thanks very much. Very interesting.
Okay.
Very interesting. Thank you very much.
Okay, any other quick burning question?
Sorry, may I ask a question regarding the notation? I'm quite confused with when you define this p comma x1 up to xn in previously.
Yeah.
Okay. They are the precisely
right.
the
Maybe
fields,
this was because I was writing too fast. I should much simpler. Yeah, I use like
okay, and they are precisely your coordinates in the tangent space, no? They are your scalar fields essentially. Am I right?
That's correct.
Okay.
Absolutely.
Okay. Okay. Good. So, thank you.
Okay.
Okay, great. Thank you everyone for the questions, and I want to thank Mauricio again for the nice first lecture. And
thank you very much. Thank you to you. I mean, that was let me stop sharing. Yeah.
Great.
Thanks.
Now